National Science Day Institute lecture. My name is Shantanu Roy. I'm the Dean Academics of IIT Delhi, and very good afternoon to you, Professor Waghmare. Very good to see you. Thanks for agreeing to give this very special Institute Day lecture. And as we know, today, February 28th, is celebrated as a National Science Day in commemoration of Professor C.V. Raman's publication, which eventually earned him his Nobel Prize. So we always try to reach out to our scientists and professors and industry practitioners who have made a significant impact in the field of science. And so we are extremely delighted to have Professor Waghmare join us today and share his thoughts on basic science of materials, enabling technologies of societal relevance. And just for the record, Government of India has declared today's National Science Day to have a generic theme of integrated approach in S&T for sustainable future. And the abstract that Professor Waghmare shared with us and which we've shared with the entire community here also kind of points to that generic theme. So we're looking forward to that lecture. So without much further ado, may I request our director, Professor Angan Banerjee, to welcome the speaker and say a few words, and then we move on with the proceedings of the day.
Thank you, Shantanu. Good afternoon and welcome to IIT Delhi's celebration of the National Science Day, or the Rashtriya Vigyan Divas. Most of you, as Shantanu has already pointed out, probably know the significance of this day. But it may be worth repeating. 94 years ago, on this day, on February 28, 1928, C.V. Raman demonstrated the Raman effect. And in 1930, he was awarded the Nobel Prize for this, for his work on the scattering of light and for the discovery of the effect named after him. If you look at the Nobel website, you can find the Nobel lecture given by Sir C.V. Raman. I quote a few things from this lecture. The lecture title is The Molecular Scattering of Light. He starts off by saying, in the history of science, we often find the study of some natural phenomena has been the starting point in the development of a new branch of knowledge. The subject started with the color of skylight, but became a passion for Sir C.V. Raman after his trip to Europe. On his trip to Europe, he says in his own words, "A voyage to Europe in the summer of 1921 gave me the first opportunity of observing the wonderful blue opalescence of the Mediterranean Sea. It seemed not unlikely that this phenomena owed its origin to the scattering of sunlight by the molecules of water. To test this explanation, it appeared desirable to ascertain the laws governing the diffusion of light in liquids, and experiments with this were started immediately on my return to Calcutta in September 1921. So it's very interesting. Firstly, the observation of a physical phenomena and starting work on this, and then the simple way in which he writes about it in his lecture. I would like to end with another quote, again ascribed to Sir C.V. Raman. He says, "The essence of science is independent thinking, hard work, and not equipment. I have hardly spent any money on my equipment." Again, different sources say 200 rupees or 300 rupees, but basically he's saying that in the present world of science, this has a special message. It is independent thinking and hard work which is critical. There are still so many phenomena that we don't understand, and clearly the message given by Sir C.V. Raman and the importance of science which we are celebrating in this National Science Day. And who better to speak on this occasion than Professor Umesh Waghmare. Professor Umesh Waghmare happens to be from my alma mater, and also again, he's a physicist, and we are delighted that he's agreed to spare time today for this lecture. So I welcome you all for this lecture, and over to you, Shantanu. Yes.
Thank you, Professor Banerjee, for your opening remarks, and may I now request Professor Ratnamala Chatterjee, our Head of Physics Department, and Professor Brajesh Mani to take the proceedings forward. Welcome, Professor Waghmare, and we move on with the lecture proceedings.
Yeah, it's my pleasure to introduce Professor Waghmare to the audience. Professor Waghmare in 1990 graduated from IIT Mumbai with BTech in engineering physics. So we feel really proud of the fact that today he has reached a stage where I will really share with all of you his achievements, and you will be able to appreciate what he has achieved in his years. He completed his PhD in 1996, and then he went for a postdoctoral associateship at Harvard University. And then in 2000, he joined JNCASR as a professor in JNCASR. So his research interests include ab initio modeling and simulations of multifunctional materials, mechanical behavior, nanostructures, topological insulators, and materials for energy and environment. He is an associate editor of Pramana, Journal of Physics, associate editor of Nanoscale, and presently the president of Indian Academy of Sciences, Bangalore. He is a recipient of DuPont Young Faculty Grant Award in 2003. He received MRSI Medal in 2004, a BM Birla Award for Physics in 2005, BAE Outstanding Research Investigator Award 2009, IBM Faculty Award 2009, SS Bhatnagar Award in Physical Sciences in 2010, and GE Unrestricted Grant for Research 2011, GD Birla. He received the India Citation Award in 2012 from the Thomson Reuters Research Excellence. In 2015, he was awarded the Infosys Prize in Engineering and Computer Science. He was recognized as a distinguished alumnus of IIT Bombay in 2017. He is a fellow in all the three academies, actually: Indian Academy of Sciences, National Academy of Science, Allahabad, and also he is also the Indian National Science Academy and Indian National Academy of Engineering. So you can see that with all these numerous awards, people have recognized Professor Waghmare as one of the outstanding researchers in the country today. And we are really glad to hear him today on such a special occasion of Science Day. We welcome you, Professor Waghmare, and we will, I'm sure all the students will benefit from your lecture. Thank you. So, Professor Waghmare?
Yes.
Hello. Yeah, you are there, right?
Yeah. Yes, absolutely. Yeah. Thank you very much, Ratnamala and dear friends and students. I'm really happy to be here with you. I wish I were present in person at IIT Delhi to have more vibrant interactions and enjoy the Science Day with you, the celebration of science. But today, the advantage is maybe we can reach out to a wider audience through online presentation. So let me share my screen and can you see my?
Yeah, we can, but you have to go to full screen mode. Yeah,
it's in full screen now.
Yeah, now it's fine.
Thank you. Yeah, thank you all. So first of all, I join others in wishing all the audience here greetings for the National Science Day, and Professor Banerjee already described what it is known for, and maybe we will touch some aspects of it during my presentation. So the purpose of my talk today is to give you a flavor for how basic science and in the context of materials enable technologies of current relevance to society. So let me get started. First of all, why materials? Well, it's not so complicated. They singularly influence our lives. And here is a history of usage of materials over a long history of human race. And starting from 10,000 BC, on the y-axis, you will see the relative importance of materials. Okay, so in the beginning, of course, most of the materials which were used by humans were the natural materials like wood, resins, and also stone. For example, this is the Stone Age. And each age that we lived in is in fact named after the material which was prevalent period. The first known metal to us is gold. Well, to chemists, it may not be surprising, but it's not hard to understand because gold is a noble metal, doesn't interact with anything, and hence is seen in its pure form in nature and easy to identify. And followed by that, there was Copper, Bronze Age, Iron Age, and we are still 5000 to 0 BC. Okay, there's a long history over which things change, and relative importance of metals kept increasing until 1950, and something changed. The trend of relative importance of various materials used by humans reversed after this point, and other materials took over. So something drastic must have happened in this period around 1950. Okay, it was a remarkable change marking the birth of material science, and we will go into some aspects of it very soon. And one thing to note is this change, I claim, is caused or triggered by quantum development of quantum physics, which was in 1900 to 1930, 40. Okay, and there's another change happening now, which is to do with artificial intelligence and machine learning, and the theme that DST has proposed as the integrated approach is going to be sort of enabled by the ideas in machine learning, and that's where we will end our talk today. Okay, so we will be spanning pretty much this period. So let me take 3 examples from history to warm up about how materials have influenced our lives and what aspects of science and engineering were crucial to their impact on our lives. So the first one is steel. Steel is something which we have known for a very long time, 4000 BC, from Anatolia, and even in India, South India particularly, we had ceramic wood steel even 600 BC. And in Africa, it was about 1.4 thousand BC. So this is known for a long time. But the widespread use of steel by humans was enabled by one specific process called Bessemer process. It's an inexpensive industrial process for mass production of steel developed in 1856. And the idea was very simple. Idea was to pass lot of air through the molten iron, which is here inside this chamber, oval chamber, and that air oxidizes the impurities in iron, such as carbon and manganese, and evaporates outside. This was a way of purifying iron on a very large scale and in a very inexpensive. And that enabled lots of changes. After that, you realize that trains were really common. Our mode of transportation, which is very crucial indicator of our development, changed. And lots of industries developed. In fact, the development of Japan and Korea largely is owed to the nanostructure steel, is the modern steel which is being processed by them in a very smart way. The second example like to give you is precipitation hardened aluminum alloys developed in 1903. And this was, there was a beautiful idea by Wright brothers to have a flying engine, flying machine. And it wouldn't have been possible unless they used this alloy called aluminum 8% copper alloy for the engine. And steel was too heavy to fly, although it was very strong. And the idea, science behind it is very simple. It's to do with solubility in solid, is temperature dependent. And when you use heat treatment to engineer fine particles of copper in phases of aluminum. For example, the melting point of aluminum is much lower than that of copper. So if you go to temperatures in between these, copper will be in solid form, precipitating in the liquid form of aluminum. And then if you cool it down, you will have a beautiful nanostructure form of aluminum copper. And dislocations and defects, which mediate mechanical behavior or plastic strain, are basically stuck at these interfaces, giving it lightness as well as strength. So this is key. Again, without this material, one couldn't fly so easily. The invention, which was so superb, wouldn't have been possible, but for these materials. The last example I'll give you from history is, again, just before 1950, is the example of jet engine. And this engine is a absolutely marvelous example of how materials impact a technology. I won't go into all the details, but would like to point out that here is a jet engine blade, which operates at very high temperatures, 1500 degrees centigrade. And that's very close to the melting temperature of the alloys that are used. And specifically what is used in blades is actually single crystal super alloys of nickel and aluminum. And these alloys are called super alloys because they retain their strength all the way up to their 80% of the melting temperature. Okay, and if you didn't have these materials, see what impact it has is you couldn't have operated this engine at high temperatures. If you cannot operate jet engine at a high temperature like this, you can't have a very high efficiency of operation. And then you can't even fly across Atlantic. So the flights which we take for granted today, which are intercontinental flights, are possible thanks to the development of these alloys over the last 50 years. And in fact, this development continues further in refining the properties of these super alloys. Okay? So these, I hope, are examples convincing enough to show how materials really determine our lifestyle and what we can really do. And after that, in 1940, 50, there was a birth of solid-state physics. The first textbook was published by Frederick Seitz. And in these 20 years, in 20 to 40, a lot of work in quantum physics, subatomic physics, electromagnetic waves, and so on happened, including superconductivity in 1911. And material science and engineering came about as an interdisciplinary science right from birth, involving confluence of these basic sciences and engineering. And one of the first departments in material science was established in 50s in Northwestern University. And MRS is not that old, it's just 1973, roughly the age of the Department of Science and Technology of Government of India. So what I'm going to now tell you is the modern materials are quite different from what we saw here. Modern materials are dominated by electrons and atoms, and that's what gave rise to this reversal of trend. After this, these are the last 70 years of history, and that's where the quantum physics really impacted how we think about materials. So material science is a syncretic discipline, hybridizing various branches as shown here, and it's first discipline which formed by fusion rather than super specialization. How the history of a material, see, this one sentence summarizes what is science of materials. How the history of materials, starting from its processing, influences its structure and hence its properties and performance. For example, it's just like cooking in a kitchen. You cook something in a little different way, the taste varies. And same applies to material. If you bake a material in a slightly different condition, a microstructure or different level of structure changes and it affects its property. And this tetrahedron is the materials paradigm. It starts with processing here at the one vortex, and it determines the structure at various levels, atomic, nano, micro scale, and macroscopic scales, which determines the properties. And properties are crucial because they involve interaction with external fields, and that determines the performance of a material in a real device application. And characterization is, of course, central to this paradigm. Experiment and theory have to go together for this to function in an optimal way. And quantum physics, I must say, approach only this particular side of this tetrahedron, not everything else. So it's a truly exciting science that affects society. And I'll start with some very simple example of current relevance. These are particularly to do with energy sector issues. And the first is renewable energy conversion. For example, you may have a catalyst which can absorb solar light and convert water into hydrogen. It's called water splitting. And in this process, what happens is the atoms in a molecule get rearranged. Here is an example of solar cell where the light is absorbed by a semiconductor and electrons and holes get rearranged to store the energy. And that energy in the form of electricity can be stored in a battery by movement of lithium ions into the cathode material as shown here. So again, any process which involves energy, of course, means there is some work done. And in this case, the work is done by atoms and electrons and holes. Here is another example where you have a fuel like hydrogen or methanol, and you burn it in a fuel cell. It generates other water and electricity. And that, of course, again involves in rearrangement of atoms or reformation of bonds and breaking of bonds. The last example is related to what I just described, efficient jet engine. In this case, the material has to be so strong that it resists any rearrangement of atoms to any external stress. Okay, so the bottom line is most properties of materials relevant to application involve rearrangement of atoms and electrons. And indeed, the interaction between electrons, atoms, and molecules and solids, of course, are key to understanding how material properties emerge from fundamental. So fundamental ingredient of a simulation or a thought experiment of a material will necessarily involve how atoms interact with each other via electrons possibly. Okay. So this is where the standard model of material begins. It's also called as first principles theoretical description of a material, where a material is just a jelly of electrons with nuclei, heavy nuclei floating in them. Here, nuclei are shown as spheres because you can use Newton's laws to study the motion of nuclei, but electrons are shown as waves because their de Broglie wavelength is comparable to the scales length scales involved, and one must use quantum mechanics or wave mechanics for that. So what one does is one observes that electrons are much lighter than nuclei and hence faster, and they remain in their minimum energy state within quantum framework. So given the snapshot of atomic positions or given snapshot of rearrangement of atoms, electrons instantaneously distribute themselves to remain in a many-body quantum ground state. And that gives rise to basically the electronic structure and also interatomic potential, interaction potential, which is the total energy of this soup of electrons and nuclei. This is the fundamental approximation called adiabatic approximation, where electrons are frozen in the quantum ground state. Is fundamental to the standard model. And as a result, in more quantitative terms, the chemistry of a material in terms of atomic number, constituents of a material, and structure, which is described by the positions of atoms, enter this total energy function, which has two parts. One is the quantum ground state of electrons, and second is just classical electrostatic repulsion with positively charged nuclei. And it's this term which is the hard part. This is relatively simple to calculate on the computer numerically. However, this is a very sort of difficult part in certain systems. But there was a practical scheme developed by Walter Kohn called density functional theory, and where the ground state energy is the functional of density and variational density, for which Walter Kohn received a Nobel Prize in '98 in chemistry. And this total energy function is the potential energy function of atoms, collection of atoms. In physics language, one would call it as the Hamiltonian of collection of atoms. And indeed, it's capable of giving you finite temperature thermodynamic properties using statistical mechanics with Monte Carlo or molecular dynamics equations. So I have basically given you the fundamental picture of the standard model as the term coined by Arvind Cohen in Berkeley. And this basically captures interatomic interactions. What do we obtain from them? We can obtain three levels of structure of a material, which is the one fundamental corner of the materials paradigm. One is the geometric structure, one is dynamical structure, and one is electronic structure. And for properties of a material are given by the derivatives of this total energy function. Okay, so indeed the relationship between structure and properties, the material's tetrahedron, is beautifully built into the standard model, which is a universal model for all materials as of now. Of course, the approximations which go in make sort of less applicable to certain class of systems than others. Okay, so this is the simple basic introduction to the standard model, and it gives you, I told you, three levels of structure with this energy function. If you just minimize that energy function with respect to the distribution of atoms positions, structure tells you how atoms are organized in real space, and they obey coordination, chemistry principles, symmetry principles, and you can of course determine this structure experimentally, and for that you need extra diffraction, whereas in theory you can just minimize this energy and predict the structure of a known or unknown material as well. Second level of structure is electronic structure. And again, these may look a little technical, but these are very basic slides today for anything in materials to understand. So typically a material has electronic states which form continuous bands because you have infinitely many atoms in a crystal, and orbitals or bands which are occupied are called valence band, and conduction band are those which are not occupied with electrons. And if there is a gap which separates conduction and valence band, you get basically a semiconductor or insulator. On the other hand, if these two bands overlap with each other, these overlapping bands are basically the highways or channels for free electronic motion. And these are metals. Okay, so this is electronic structure. Experimentally also can be determined using spectroscopies, but this is a direct side output of density functional theory standard model calculation. The last aspect of structure is the dynamical structure of a material, which basically is done by vibrational spectrum or phonon dispersion, where just like electrons, vibrations in a crystal are also waves, and atoms are oscillating in time. And this structure tells you how atoms are organized in time around the equilibrium structure. So these are vibrational frequencies, and x-axis is the inverse wavelength. And you will see these are acoustic phonons. The slope of them give you elastic moduli, and they tell you how fast sound propagates through the crystal. The strength of these modes, these are optical modes. They tell you how stiff are the bonds in the material. And Professor Banerjee referred to Raman spectroscopy. Raman spectroscopy gives you just one of these points, okay? Whereas vibrational spectrum of a material is very rich. It has lot of wealth of information, and Raman and IR spectroscopy give you basically these uniform vibrations in the material. Of course, if you do second order Raman, which is even weaker in intensity, you can have access to this. But if you really want this dispersion to be accessed from experiment, you need inelastic neutron scattering, and hence a nuclear reactor. Whereas in theory, we can derive it essentially as derivatives of energy, and within a few hours, one can do this calculation for simple systems. So the same vibrations determine the thermodynamic stability of atomic structure of a given solid. Okay? So these are the three levels of structure that are accessible from the standard model. And of course, the properties that can be correlated with these different levels of structure of a material or a molecule. So let me move on. Many computer programs to do such standard model first principles calculations are free and can be downloaded and be used easily on any small computer even. And even with moderate resources, one can do a lot of interesting exploratory research problems that I'll demonstrate to you. So materials for technologies. Now I'm getting into the main theme of the application of the standard model. And I will highlight to you how materials are crucial to technologies and that can tackle the current challenges of the society. And I'll start with the first example to do with renewable energy conversion and storage. And of course, intimately linked with climate change or the global warming. And specifically, I'll be focused on one aspect called carbon dioxide reduction and utilization. And this is where I will demonstrate how basic science can really be used to tackle the current challenges. So if you look at the energy and environment, on this figure, what is shown is the emission of carbon dioxide in percentages of different types of applications. One would imagine that cement was one of the dominant factors, but not quite so. But you will see much of the CO2 emission comes from generation of heat and electricity, and specifically the coal power plants, thermal power stations. And second is the short distance road transport, like vehicular transports within the city elsewhere. And then you will see the other sources of CO2. This is called anthropogenic CO2 generation, and you will see this is taken from X-Prize. We are living in an age of innovation, unprecedented era of technological progress, which is primarily driven by energy. However, most of the energy comes from fossil fuels, such as coal, oil, and natural gas, that account for huge amount of CO2 emission. And we know now that CO2 emission are a leading contributor to climate change. The world will need a portfolio of solutions to address this challenge. And that's what we took up. So here is a schematic which shows that energy usage actually reflects on how developed our society is. And unfortunately, if you go with the current sources of energy, they invariably generate a lot of carbon dioxide, which is a greenhouse gas, and also heat. Heat is basically the dissipation, waste energy, wasted part of energy, which cannot be used easily. So these have negative impact on the environment, and indeed, although in short term it may look like we are developing, in the longer term it may have adverse impact on our development overall. So this is the first challenge I'm going to describe. So it is necessary to have clean energy sources, and given that fossil fuels are sort of diminishing and global warming have prompted, which is associated with usage of fossil fuels, prompted the need and use of renewable energy. However, you will see that these sources of energies are intermittent. Solar energy is available only on sunny days and not in the night, whereas you do need energy all through. So second part of it is we can't overnight make a transition from fossil fuels to this renewable energy technology. So to make that transition, one of the intermediate solution is can we do carbon fuel recycling? So we continue using fossil fuel, but minimize its impact on environment, global warming, climate, and at the same time generate the fuel back. That's a very beautiful idea, and that's what is shown here. And the schematic described in one of our recent perspectives, where one would like to use solar energy as a renewable source of energy, and one would like to minimize this greenhouse gas CO2, which is generated in factories and thermal power stations. So idea is to use solar energy to split water using photocatalysis or photoelectric catalysis to generate hydrogen. Hydrogen is a green fuel because you can burn hydrogen, generate energy, and gives you back H2O. So it's a completely recyclable fuel, and hence it's green. There's no pollution involved. But instead of doing that, the problem with hydrogen today is we can't store it efficiently to use it vehicles. Like I described, the second source of generation of CO2 is vehicular transport. And unfortunately, there we need to go back to carbon-based fuels. So what the technology proposed here is the CO2 is reduced by H2 as a reducing agent using thermocatalysis, using the heat generated in these stations, also as a waste, and result in methanol, which is a fuel. Of course, it's a carbon-based fuel, but it's an easily portable fuel. In a way, it amounts to chemical storage of hydrogen. Hydrogen is dumped into this chemical. The advantage of methanol is it can be used in our automobiles in the way they are today, without modification of any engine. Maybe one needs to modify a few pipes because it's a little more corrosive than gasoline. And whatever emission comes from the methanol possibly should be captured using carbon capture technology and recycled. So this achieves carbon recycling in some sense. Okay, and 1 kg of CO2 and 0.14 kg of hydrogen, about 0.73 kg of. Well, this is very appealing because it addresses the global warming aspect, climate. It uses CO2. It recycles fossil fuel in some sense because the CO2 which is generated is converted back to a fuel. And third, solar energy intermittency is also addressed because you store solar energy in hydrogen which in turn gets dumped into this chemical form of energy, methanol. So energy storage problem is also addressed. It's a very beautiful solution. You need two materials to do this. One is the photocatalyst, which absorbs renewable energy, solar energy, and splits water to hydrogen. And second material is the thermocatalyst, which performs CO2 reduction, and that's a grand challenge. Okay, this technology is relatively developed, but this one requires a lot more work. So, idea is these two materials enable technologies which involves hydrogen generation, hydrogen storage, carbon recycling, and CO2 capture / I won't be referring to capture, which is already reasonably well developed, okay? But it's the reduction which is key aspect that we have. So here is a sort of first part of it, which is the hydrogen generation using solar energy. There are, of course, two routes. You can use the usual photovoltaic solar cells to generate electricity, and that can do electrolysis of water and split it into hydrogen. The other route is directly use photocatalytic material, which absorbs solar energy and converts it to chemical form of energy by splitting H2 hydrogen as the fuel. So, of course, in this short presentation, I can't go through every aspect of it, but I'll tell you what we could do in this simple site. So, desirable photocatalysis semiconductor for water splitting to generate hydrogen should absorb the energy from solar radiation efficiently. So, its gap should be as small as possible, but it cannot be too small because this semiconductor has a conduction band and valence band. If you absorb solar radiation, it generates a hole, an electron pair, and this electron is used in reduction of hydrogen in a hydrogen evolution reaction to generate H2 molecule, and the same hole is generated in oxygen evolution reaction, which whose redox potential has to be just above the valence band, and the redox potential of HER has to be just below the conduction band. And the gap between these two redox potential is 1.23 eV. So the gap of a semiconductor has a lower bound of 1.23 eV. So we can't use this part of the radiation. However, if you can absorb these and you have a semiconductor which can do this magic, you can split water into hydrogen, sort of photocatalytic manner. So we predicted a simple material, two-dimensional niobium nitride, which was a single material which can be used for both photovoltaic application in solar cell as well as direct splitting of water to generate hydrogen. Of course, there are many works which have been done, but this I'm giving you my own example where this standard model of first principles calculation of materials can be used in prediction of a new material. Now, the second part is the catalytic activity for CO2 reduction, and catalytic activity is determined by interaction between molecular species and the surface of the catalyst and created by electrons. So this is where we use the quantum physics and powerful computers to simulate it. And basic idea is you want to start with a reactant and arrive at products AB. And to do that, there is usually an energy barrier to cross, and that energy barrier decides the rate of reaction. Whereas if one does that reaction on a catalytic surface, this barrier is reduced. Okay, and that's how the catalyst works. It doesn't really change itself in the reaction process, but it facilitates a chemical reaction. This is a very simplified textbook sort of description, but in real catalytic reaction, there are several steps which go up and down, and from one step to another, one has to go through this transition state. So real analysis is much more complicated, and in the catalysis of CO2 reduction, we want to, a very challenging problem because you want a target product as methanol, not other products. One can easily get carbon monoxide by reduction of CO2, which is not a favorable product. One can get other type of degradation of catalytic material because of CO2 and poisoning. One can get methane or ethylene, and none of these are desirable products because we want single product methanol, and that's what is called as selective synthesis of methanol. The catalyst should be cyclable, means it shouldn't degrade. It should be scalable, means we shouldn't just work in the lab. It should work at very, very large scale. And it should be economic because otherwise we can't scale it up to large scale operation. In industrial scale, we will be converting thousands of tons of CO2 to methanol in a given month or a year. So set up infrastructure for this for actual reduction. So intermetallic copper-based catalysts are known to be relevant in this case, and we basically use machine learning as well as quantum methods to do this design of material. And there was a startup company I was co-founder of in 2016, Breathe Applied Sciences, which basically combined experimental theory to sort of attack this problem as a part of fixed price competition. Again, this is a colloquial talk and I won't go into technical details, but this is to tell you how complex this process is. When CO2 reduces to methanol, it passes through 6 steps of proton addition to the various intermediates. And when that can happen in a number of different ways. It can happen through carboxylic acid group or format pathway or RWGS type of pathway or trans CO2. So when one does theoretical analysis, one indeed needs to consider all these pathways and determine which one is the most favorable for a given choice of catalytic material. And as you can see, it needs a lot of computation. And that's where we also leverage from machine learning. But the kind of diagrams we can get from the standard model calculation is we look at the surface of say, nickel indium, consider various possible steps, and then determine the kinetic energy barriers for each step. And what we could show is, for example, although this is the transition state which has a high barrier, the rate limiting step happens to be TS1, where this pathway is favored because it has a much lower energy than carboxylic pathway. So this forms a starting point in going about engineering this catalyst further to improve its performance. The work is now being continued by Breathe Applied Sciences to scale up the CO2 reduction plant. In fact, in last January, the Breathe had capacity of 300 kg per day CO2 reduction to ethanol, and now they are in the process of. I'm no longer with them because most of the work now is being done by Sebastian and Lakshmi. So this was the first example I wanted to give you, where really the basic sciences can be leveraged in addressing grand challenge problems faced by society. The second example I would like to give is materials for technologies to tackle basically the challenge of wastage of energy and how we can use wasted energy into a useful form so that it again alleviates the energy issue in a significant way. And the waste form of energy, sorry about this, thing here, is heat. Heat is omnipresent. Everything we do involves heat, thermodynamics, and how we can make use of the wasted heat. If we can, this is our dream, that these are the chulhas in remote villages of India where the power lines cannot even go to supply them electricity. But suppose they do have a chulhas possibly based on wood or other sources of fuel, we want to develop a material which can attach to these chulhas and convert it, light up a lamp in their hut. So this is basically electrifying remote villages without having to send power line all the way there and eliminating the maintenance of those as well. And these materials are called thermoelectric materials. They can convert waste heat into electricity. The beauty is they don't involve any moving parts, so maintenance is very little. Of course, they need to be very efficient. In principle, any material is a thermoelectric, but not most of them cannot be used in practical applications like this. And thirdly, it should be available in India. For example, copper sulfide in copper mines. Okay, so this is the project we have. This is in collaboration with a group in UK, where we are developing materials based on Indian resources, which can tackle this problem for remote villages. So what is the basic science of this? Very exciting. Basic science of thermoelectrics involves really interesting science challenges. So thermoelectric is a material, if you sandwich it between heat source and the heat sink, it can generate electric voltage. And and that voltage is proportional to the temperature gradient you have, and that constant is basically the Seebeck coefficient. So larger the Seebeck coefficient, larger electrical voltage you would generate across this. The next is electrical conductivity is very important because the material should carry the electrical current very efficiently, but not the thermal current. See, this is the key. If the material carries heat very efficiently, most of the waste heat will be carried to the heat sink or the cold part of the body, right? And that will not be efficient thermoelectric. So for an efficient thermoelectric, you need a very low thermal conductivity, ultra low thermal conductivity, like a glass. If you need a high Seebeck coefficient like a semiconductor and high electrical conductivity like nickel. So a single material should behave like a good metal, good semiconductor, and good glass in different domains of properties. If you can develop a material like this, you can also use it to refrigerate things. So in the villages where you have chulas, you can also have a fridge attached to it, which will be using the heat generated by chulas and cooling it down by basically rejection of heat. Okay, so it's a very appealing materials which can enable technologies. So these conflicting requirements are shown here in a more quantitative sense. So Seebeck coefficient, as you will see, is directly proportional to effective mass of electron carriers and inversely proportional to the density of these carriers. On the other hand, electrical conductivity is directly proportional to it, inversely proportional to the mass. So the numerator of this figure of merit, which is called the power factor, because this is voltage times current, right? That is basically involving conflicting optimization. If you optimize S, you minimize sigma and vice versa. And not only that, if you minimize sigma, you increase sigma, the electrical conductivity, you also increase thermal conductivity, and that work against you as well. So that's the scientific challenge. There are opposite trends that we need to meet, and this is a typical thermoelectric. You will see in low carrier density, one has semiconductor with high Seebeck coefficient, but it reduces notably. For a metal, you have high electrical conductivity, but which reduces semiconductor. So in between, you have higher ZT, but that ZT may not be high enough for people to find it useful. So that's the science challenge of development of material, which we do this thing. So the recent work which we did was published last year in Science, involved very beautiful science of disordered crystals in solving this problem. Okay, so what is known is typically you have a valence band of a material and a conduction band of a material, and if they overlap with each other, you have a metal. But in certain materials, you can have disorder. Disorder means atoms can be randomly decorating the lines. And if that happens, these are called edge of the band states, which become localized. And that's called Anderson localization of the states, which is localization of electrons at the band edges in adequate disorder in 3D. And once you have disorder, and if your Fermi energy of a material here, you have an insulator, no high conductivity. But if you dope it, you can move the Fermi energy down. This is called as the mobility edge. Once you cross the mobility edge, you can have a conducting semiconducting material, and vice versa here, 8 types. Okay, so what our experimental collaborator Kanishka proposed is we can engineer the disorder. That's why it's called atomic engineering of a material. You here is Ag silver antimony telluride. It's a crystal, single crystal, where antimony and Sb are randomly distributed at the same lattice size, and that causes the disorder. Okay, it's called anti-site disorder, and that gives you this localized. Okay, so achieving optimally high disorder, which will maintain semiconductor character as well as high conductivity is what we achieve. So how do we, this disorder has effect? This is a perfectly ordered electronic structure of antimony silver telluride, which is almost semiconducting, very metallic, the overlapping balance. Right? But moment you introduce disorder, you get these states which are in the gap, and those electronic states you will see are localized on the defect side. These clouds essentially indicate electron clouds in the crystal calculated from the standard model, and they are highly localized on those defects. Whereas in infinite crystal, perfect crystal, they are beautifully extended all across the crystal and carry electrical current. So can we engineer this disorder in AGSBT2? So that's where what we found and showed theoretically also is if you dope cadmium in AGSBT2, it's interesting because of the size of cadmium and the charge of cadmium, it prefers disordered sites of antimony. And don't go into this complicated figure. There's a lot of information in it, but this is to convince you that the standard model calculations give you this energy, formation energies, which allow you to tell whether a given doping will reduce disorder or increase disorder. And what we showed is cadmium atoms replace disordered besides selectivity, and hence improve the percentage of ordered sites. So this is where experimental is used and showed, of course, these are all calculations with cadmium doping, we could eliminate those defect states and get a beautiful semiconductor. Okay. Not only that, we could get many more bands of the conduction and valence edges, and that is called band convergence, which enhances the coefficients, and also this enhances the electrical conductivity by delocalizing the electron associated with it. So this was the idea, and as a result, we also showed basically once you substitute cadmium in this crystal, it distorts the lattice locally because of the size of cadmium is different. These arrows indicate displacements of atoms near cadmium, so it develops a local strain. So you have a crystal where locally nanoscale region is slightly deformed, lattice mismatched. When there is a lattice mismatch, the sound waves which carry the heat basically get scattered by those regions. Okay, and that scattering is given by phonon coupling. So interaction of cadmium scatters phonons through large coupling between low energy phonons and the local strain which are developed near the cadmium site, and that basically reduces phonon thermal conductivity, which is the dominant mechanism. So this strategy of enhancing ZT in this compound is quite general. So this route says you can do atomic scale engineering to optimize thermoelectric performance. So now we are using this scheme in the Indian context, where the materials which are focused on is chalcocite, which is the sulfide of copper, and digenite, which is copper deficient sulfide of copper. And these two are intrinsically disordered because copper sites have copper atoms have too many sites in the crystal available to occupy and the number of copper atoms. So this site occupancy disorder attracted us to the science of these materials, and also the fact that it's non-toxic, it's abundant locally, and it's inexpensive. So if we succeed now in doping this and developing an optimized thermoelectric, we should be able to go back to remote villages and help in electrifying their houses using the waste heat. Next, I will, so this is the disorder associated with lastly, I will go to the example where we are tackling a problem which involves interface between physics and electrical engineering and electronics. So these are materials for technologies to tackle enormously growing data, which is really big problem today. The amount of data you accumulate on your mobile phones or other media is just exponentially growing, and what one would need is, of course, efficient data processing tool, which is where machine learning is powerful, but also we need efficient data storage. Why? Because if you see today, a huge amount of energy is spent on data centers, which basically house the data that you are accessing from various parts of the world. And storing big data will be facilitated if we will alleviate the energy challenge. If we have a very high density data storage, which is spatially efficient data storage, very high speed, fast access, and hence it should be energy efficient. So can we think of a material which will solve these problems? And ideal if the material can be readily integrated into. So here is where I'm going to introduce you class of materials called Phenoelectrics, which allow you to store data using electric dipole movements. So these materials are class of the special class of piezoelectrics, which have electric dipole in it, just like a magnet. And if you apply mechanical stimulus, they generate electrical signal, and you can light up a lamp, for example. This is called piezoelectric effect. In the inverse effect, one can apply electrical signal and make a material vibrate. And that's what is given the effect used in our speakers, where you can use AC voltage to generate sound waves and hear what is, for example, the music for various. Ferroelectrics is a special class of piezoelectrics where this dipole moment can be switched to opposite orientation by applying large enough electric field in reverse direction. And because of this dipole moment doesn't vanish, even if you switch off the field, you can use the direction of this dipole moment to store binary information bit. And hence, it has lots of applications. So at atomic scale, a typical ferroelectric looks like this, that we have a cubic structure of, for example, barium titanate, where titanium atom is at the center of this hadron of oxygen. This is beautiful cubic perovskite structure. And as you lower it, you get a low symmetry phase hexagonal structure where the titanium atom gets off-centered spontaneously in the low temperature phase, giving a dipole moment because titanium is positively charged, oxygens are negatively charged. And this up movement gives you dipole moment where you can store the computer data with 1, and the reverse polarization where the titanium goes down, the dipole moment down, it allows you to store the information 0. Okay, and it's a non-volatile computer memory, and it of course also involves phonons. Ferroelectricity, unlike magnets, is very sensitive to surface, and hence we don't see that in day-to-day life. And at nanoscale, it becomes even more interesting because this electric polarization generates these monopoles. See, in magnets, this is not so simple. Magnets don't have magnetic monopoles, whereas here, the polarization generates the surface charges, and that creates opposite electric field, which can suppress the dipole itself. And what is known from experiment is, as well as theory from my group, is at nanoscale, a ferroelectric actually decomposes into inhomogeneously ordered state, domain structure, where dipoles are up and down, up and down. This is called strike domain structure. And unfortunately, this cannot be used for memory application that I talked about. Okay, so although these are very technologically important materials used in sensors and actuators, which is a $1 billion industry, you can't use them for the high density storage that I motivated. So this is our motivation. So how do we go about solving that problem? And basically, control over domain structure is very crucial at very small scale, and which material would be relevant. So that's where we stumbled upon hafnium oxide, which is an oxide which is already used in field effect transistors as a dielectric material. But if hafnium oxide is grown in a specific crystal form called orthorhombic crystal structure form, it is ferroelectric with very exotic ferroelectricity. Unlike barium titanate, here the ferroelectricity is driven by oxygen atoms, not hafnium. Okay, so it is readily integrated into silicon. And what we will show is it has very ultimately high density memory. So in hafnium oxide, the origin of electric dipole moment basically involves displacement of oxygen atoms in the system. And there are 2 types of displacements which are involved. One is the parallel displacements of oxygen atoms here, and the second one is anti-parallel displacement of oxygen. And they both, what is magic about hafnium oxide is, by the way, hafnium oxide structure is very similar to zirconia that many of you use in jewelries. So this crystal structure is exactly the zirconia, cubic zirconia structure. But once the magical thing about hafnium oxide is both sets of displacement equally mixed together to give you the ferroelectric wave. As a result, in half of the oxygen atoms in one you get zero displacement. It's a large dipole moment called the Phenoelectric Effect. So this is a three-dimensional architecture of hafnium oxide, which allow you to have two-dimensional electric dipole sheets, which are confined within 0.27 nanometers. You know, that's amazing. And it's purely anionic ferroelectricity, novel type of ferroelectricity. What is more spectacular is you can switch one oxygen sheet down with dipole moment down, and it has exactly the same energy as the uniform polarization, and it passes through a huge barrier. So if you have one dipole switched or two dipoles switched, you see two sheets of electric dipole, you have the same energy, which is separated by a large energy barrier. This is very different from barium titanate or lead titanate, where if I try to switch one dipole moment, you know, it spontaneously goes into a much bigger domain. And that's the domain wall, which brings up and down polarization. So lead titanate cannot be used for such ultra high density application because it has very small barrier to go from one unit cell dipole to another. Whereas in hafnium oxide, each dipolar sheet can be switched and be used to store memory. So you can have 2 bits per nanometer memory application device. The second thing where hafnium oxide stands out in terms of its ferroelectricity is all conventional ferroelectricity have very low coercive electric field, switching field, in comparison with our activation field, whereas in hafnium oxide, the two fields are equal. And the reason for it is ferroelectricity in hafnium oxide is basically scale-free, and it means you can have ferroelectric dipole sheets at any length scale that you like, and it's equally. And as a result, there is no size limit on ferroelectricity in hafnium oxide, neither lateral nor transverse. Okay, and as a result, ultimately high density storage devices can be developed using hafnium oxide ferroelectricity. And here is our theorist imagination that if you can have the beauty of hafnium oxide is you don't need a technology to nano pattern it. Like in semiconductor memories, you need patterning of a material, active material at small scale. In hafnium oxide, it's not necessary because the 3D architecture of a crystal itself supports ferroelectricity scale. So all you need is deposition of electrodes on a small enough length scale. If you can deposit electrode and connect on a half a nanometer, you will have the ultimately high density. And even if you say with the present developed deposition technologies, one may have to have several nanometers of width. Sure, this is still 100 times growth in the density of data storage that one can achieve using ferroelectric oxide. Of course, there are still challenges to tackle, and this is sort of just the beginning. As you know, when a material is realized with some interesting property, to deploy it in technology takes a lot of time. And translation into realistic application always takes time. So I'll stop here in terms of highlighting how the standard model works. I'll just summarize that it is indeed been very powerful. It understands puzzling experiments, complements experiments, in accessing information which is not easy to access experimentally, and it can also predict new materials or new properties in example. So it's really indeed predictive and powerful. However, it has limitations. Okay, I don't mean to give you just a glorious picture of this standard model. Unfortunately, the predicted material structure is often not so easy to synthesize in a scalable way. And given a material structure, relatively simple properties can be predicted, like I explained to you, ferroelectricity, elastic moduli, and so on. Real application and deployment also needs one to assess how does a material fail due to repeated application usage, repeated stresses. And that requires much higher level of drilling. For example, the material I told you used in jet engine has a life of 30 years of shell. And nickel aluminum alloys allow this operation at high temperature. But one can't be sure after 30 years. And there's no simple way I can use quantum physics to predict how this material ages. Similarly, the breakdown of battery material, as you know, some batteries explode even. What leads to degradation of voltage of a battery with time? And that's a long time scale, length scale problem, and may not be easy to access this standard model. Okay, and that's where we need to take help of more encompassing scheme, and that brings me back to the DSC theme of integrated approach. So basically, I'm summarizing the materials paradigm, and first principle standard model gives you connectivity with these two things, but the processing of a material and its performance are also very crucial, and you need integrated approach to capture all four. And that's where machine learning based approach is becoming very powerful. And that's where, you know, one wants to use data on synthesis as well as composition and various properties, various structural details, and how does data relates to properties, that target property material, and that functional relationship is what will be derived using machine learning from learning from this data and otherwise. Here, experimental theory have to go together because, you know, so far theoretical data alone has not proven. Okay, so let me summarize my entire presentation. I won't summarize specific details, but the take-home messages are indeed the basic science and research are key to development of new technologies which are of relevance to the society. And specifically, I highlighted how material science is very rich. It's a multi-scale interdisciplinary science and engineering which impacts most aspects of society. And science is an exciting enterprise, not just material science. It's a robust way of thinking. And on the occasion of National Science Day today, I take this occasion to encourage you all to be engaged in it throughout your life. I acknowledge my collaborators with whom I had done some of this work, the PhD students and postdoc, Meghna, and the experimental collaborators from JNC, Kanishka Vishwas, Das and CP Vinod, Sebastian Peter from JNC who worked on CO2 reduction, and he is continuing the Breathe company further. Ajay Soni from IIT Mandi and Zain from Shenzhen. And the last work on memories was done with Judy Lee's group at Ulsan and Achay University. Wish you all my greetings for the National Science Day. Thank you very much. I'll be happy to interact with you.
Yeah, so now session is open for question and answer. So I will begin this session by thanking Sir Waghmare for very knowledgeable talk. And I must say that while I was a student, I had opportunity to hear him many times. And each time I hear, I learn something new. So that is one of the good point about his talk. He goes to such a detail that for students, it's very informative. So yeah, so what we'll do that, so we'll have a first question from the WebEx, and then we'll have a question from the YouTube. So yeah, if you have any question, please raise your hand, and you can go ahead, you can ask the question.
Ashok Ganguly.
Yeah, Professor Ashok Ganguly, yeah, please go ahead. So let me...
Hi, Umesh. Very good talk.
Yeah.
Thank
So,
you.
I have two small questions. One is kind of your hexagonal niobium nitride.
Yes.
Was that a theoretical work or that was on thin films?
It's a purely theory prediction.
Okay.
The material.
You predicted high thermal disorder in that, right?
That's no. Niobium nitride is where we showed that it has an electronic and phonon structure, which makes it suitable for both photovoltaic applications as well as catalytic splitting of water.
Okay, both hydrogen as well as it is a good photovoltaic material.
Yes.
That was a theoretical work. But
yes, it's the next generation solar cells in the sense. I couldn't go into details, Ashok, but it's such a beautiful system. See, what happens is when solar light is absorbed by a semiconductor in a solar cell, you will wonder where is the efficiency limited for? And one simple answer to even a high school student is, well, much of it gets wasted into heat. Yeah, and that wastage into heat is basically through decay of electronic excitation into vibrations, phonons. Okay, and this material has a gap between optical phonons and acoustic phonons, which is larger than the largest acoustic phonon frequency. So it avoids what is called as Clemens decay, means even if electrons will lose some energy to optical phonons, they cannot lose their energy to acoustic phonons, which can carry the heat away. So you can have high temperature device which will operate at very good efficiency.
So this is realized experimentally?
No, not yet.
Not yet.
Well, yeah, we wrote one more paper, Ashok, on the same system where we showed it can be an electronic ferroelectric if you stretch it a bit. So that came in PRL in 2019. So it's a very interesting material, very unusual bonding in it. And it's also superconducting if you can do it in square form. More interesting to you, I suppose.
So my next question is this HFO2, hafnium oxide.
Yeah.
What is it? Why, if I have to because if you take cubic zirconia and I want to convert it into the property of HFO2, because hafnium is expensive. So suppose I want to make it scalable and large scale. If I have the trick, so what is it that cubic zirconia, is it the phonons which are, is different in cubic zirconia compared to cubic hafnia? What
Yes.
I have to tune so that I move towards hafnia in property from zirconia. So I give zirconia, it can be thoria also, something which has the same structure, but I move it in the lattice part, the lattice vibration part, I move it towards hafnia. So do you think my mind is working in the right direction?
Absolutely, Ashok. And in fact, that's why the paper could get through science. The physics of it is very fascinating. And we call this the physics of flat bands of phonons. Flat bands of electrons are very fashionable in twisted graphene. But here what we showed is the phonons of hafnia the bands are relatively flat. When a phonon band is flat, what it means is basically the interatomic interactions are weak, meaning it's like time binding hopping parameter, but for atomic displacements. Whereas in zirconia, the phonon bands are not so flat. Okay, so one need to think if you want a descriptor for design, and in fact, the Korean group is now following this up. They are looking at substitution of silicon, and even in the United States, people are looking at zirconium substitution with other elements.
It's possible.
To make it more like hafnium.
Thanks.
Yeah, Professor Khare, Professor Neeraj Khare.
Yeah, okay. Hello, okay, Umesh. It's a very nice lecture.
Thank you.
I have one question this related with the thermoelectrics. It's a very nice scheme. You suggested that by introducing disorder, it is possible to really get high Seebeck coefficient and also somehow balance the conductivity. So my question is related with this, that suppose you make these material that you are talking about in the form of bulk, or you make in the form of film. So will still you can maintain the same kind of good quality as a thermoelectric material?
Yeah, that's a good question, Neeraj. When you have a film and you possibly would have the boundaries between particles in a film, there will be additional scattering that is relevant to the thermoelectric performance. But typically, my expectation is the thermal properties won't change that drastically. If anything, they may improve in the sense thermal conductivity may go down. The analysis that I showed and also the experiment was for single crystal. On the other hand, the electronic properties, the interface is unusual for electron transport, particularly when you have balance and conduction bands and too many of them converging together. So that part I'm unable to predict what may happen in a film form.
Okay, so my second question is what should be kind of threshold ZT value or some kind of power factor which can really be trade-off for this different application like Chula application that you were talking about?
Yeah, for Chula application, one would need ZT of at least 1 at a temperature which is around 500 degrees centigrade, and second would be room temperature.
Okay. Okay. Thank you, Umesh.
Yeah, but in the absence of that, one may still be happy using lower ZT also. It depends on the cost also. See, it's finally economics, which material is inexpensive and at the same time can replace some electrifying technology solution.
Okay, fine. Thank you.
Okay, any other questions, comments? Okay.
Hi, Brajesh, can I ask?
Yeah,
Yes,
yeah, please go ahead. Yeah.
Okay. Hi, Professor Waghmare. I mean, it's really inspiring to hear you. I'm also hearing you since from my early PhD days. So it is always really, really nice. So maybe I'm asking you a bit technical question. The thing is that in your thermoelectric part, as you said that you are basically trying to tune both the electrical conductivity vis-a-vis the thermal conductivity. Now, once you are doping this cadmium, as I understand, you have to go for a big supercell because you want to localize the defect for obvious reason. Otherwise, the defect will not get localized. Now, in the process, once I see your band structure, the band structure is little bit having band folding problem is there. Now that is obvious because you have gone for a supercell effect, and that is what it is happening. Now, if it is a pristine system, you can unfold the band. That's not a big problem. But since you are doping, so you have basically destroyed the symmetry
across different points.
Correct. Thank you very much. But in K.P also, you mean to say you want to plot it using tight binding or just
K.P can be done within DFT. So the codes which I refer to in my slides facilitated that type of analysis. I would recommend Abhinit for that.
Okay. Thank you very much.
Okay. Any other question from the people who have joined through WebEx?
You can tell that we have several students.
Yeah, so we have a lot of PhD students sitting here. In fact, many more wanted to join, but we told them to come in a limited number because we wanted to maintain this social distancing. So we have one student, PhD student sitting with us. He wants to ask one question. Yeah, so please tell us your name and then ask.
Sir, myself Manjari Jain, and thank you for a nice presentation. So my question is related to that photocatalyst. So for photocatalysis, it's two-step HER and OER, and for HER it is like less than 0 electron. The band gap should be in the range of 0 to 1.23 electron volt. So my question is like, if for HER, if the band alignment is less than 0, but for the alignment for 1.3 electron volt is less than 1.23. So are these materials are promising for that photocatalyst purpose or not? Like both the conditions are required for that purpose, or any of the either of the condition is prominent?
Yeah, if you would like to use the same material for the complete reaction, means both half electrodes, then you would need both the conditions to be satisfied. You can, of course, use different electrodes, and then the condition may need to be satisfied by the respective material.
Okay, so it means that I can use my material for HER only and for OER only as well.
Yes. If you have one of the offsets not correctly given, yeah.
Okay, thank you, sir.
Yeah, any other question? We have a couple of more minutes.
Yeah,
maybe
Divya Prakash wants to ask.
Yeah, Divya Prakash.
Yeah. Good afternoon, sir. Myself, Divya Prakash, student under Professor Rasma Chatterjee. And I am interested to know whether the theory of thermoelectrics will work on a very good note when we are working on a superconducting material. Means if someone is interested for superconducting thermoelectrics, how the theory will evolve or change in the superconducting regime.
Wow, this is an amazing question.
Very interesting. Now
Very
you think
interesting
about
question.
Cooper pairs first.
That's right.
Not electrons, but you need to think now Cooper pairs.
So maybe Ashok is
DFT. Okay, yeah.
yes, MD and all basically is the standard statistical mechanics.
Yeah. That's correct. So I was just wondering that when we predict the properties using DFT, then very often it is not in the experimentally relevant condition. For example, the thermoelectric material, we are citing the results which are finite temperature, and our simulation predicts at the 0 Kelvin. So then we have to go beyond this DFT, and that's where MD and MC comes in. But not in all the cases, it is very good to develop this kind of method because it's not possible. So what is your prescription that how should we move towards that direction? Because this first principles force field Hamiltonians, as you know, it's not very easy to develop in all.
So there are many advances in recent years where people have extended DFT-based phonons to finite temperature phonons. These are sort of mean fieldish analysis. See, molecular dynamics on MD don't help. Because even if I have force field for you, because the thermal conductivity to be very low, and the scattering mean free path, they tend to be sort of outside the reach of this MD calculation. The time scale is small.
Yes.
Often. So what helps is basically to get hints from these fundamental calculations and use phenomenology to relate to the observed properties, which of course are at finite temperatures.
Yes. Okay. Thanks. Yeah. So shall we?
Thank you. I will really need to stop soon.
Yeah, thank you, Professor Waghmare. Actually, definitely I had a question, but I think we will discuss it one day on Skype. So it was a wonderful talk, and you can see from the question that it was very interactive too. We are very happy in the physics department that you could take time off and really basically tell us so much about exciting prospects of this kind of theoretical research for experimentalists. And this is what is driving today's physics. And today's students actually have the advantage of using both. And that is something which is marvelous, and it has come through your work. Actually, I was quite impressed with your Chula work because it's something which would never, I mean, we also work on thermoelectric effects, but I never thought of really using that Chula waste energy to be used. So it is really impressive. And thanks a lot once again.
Thanks.
Thank you. Good night.
Bye.
Bye.
Shall we stop now?
Yeah.
Yeah.